Daniel Spruch to campus. Dr. Spruch has received his PhD at Tel Aviv University in 2010. And since 2010, he's been a postdoctoral fellow at Ben Gurion University and the Golem Assistant Professor of Mathematics at Purdue, and is currently a visiting assistant professor at Indiana University. He's here to talk to us today about Shahidi local coefficients and irreducibility results on coverings of P-adic SL2.
Hello, good afternoon. I would like to thank the hiring company for this opportunity. So I spent the day here in this really lovely department. I'm really happy to be here. I'm a representation theorist. The kind of representation I like to study lies in the field of automorphic form. Precisely, I'm doing the P-adic end of this. So I'm studying representation of P-adic groups. Moreover, covering of matrices groups. A typical problem in representation theory is that you are given a vector space, complex case, vector space in my case, on which a group acts, and then you are asked, is there an invariant subspace? And the kind of problem I like to solve, you end up studying the analytic properties of some meromorphic functions. After giving you a short tour about the P-adic numbers and their role in number theory, culminating in the local portion of Tate's thesis, I will discuss a problem that was solved probably in the 70s, and then I discuss a related problem, the problem I solved along with David Goldberg. So it all starts with the absolute values on Q. So an absolute value on Q is a function from Q to the non-negative real numbers, which satisfies triangular inequality, multiplicativity property, and x has absolute value 0 if and only if x is 0. And the familiar example is the Archimedean absolute value, the one which eventually gives you the fields of real numbers when you take a completion. Here's another example, the trivial absolute value. And let me give you infinite families of absolute values. Given a prime number p, we define the P-adic absolute value of Q as follows. Any non-zero rational number can be written as some integral power of p times a over b, where a over b are integers which are relatively prime to p. So we set the P-adic value of x to be p to the minus n. And it is not too much of a hard exercise to verify that indeed it is an absolute value. This exhausts all absolute values on Q. The P-adic one and the Archimedean one are essentially all non-trivial absolute values on Q. By essential, I mean if you take any other, you will get the same topology. There are no more topology you can create this way. And then, towards the turn of the century, Hansen constructed the field of P-adic numbers. The field of P-adic numbers is defined to be the completion of Q with respect to the P-adic absolute value. Namely, exactly the way you construct R. So, QP has a distance, which extends the distance on Q, the P-adic distance. Q is dense there. Any Cauchy sequence of P-adic numbers converges to P-adic numbers. Okay. On one side, on one hand, this is a very analytical object. When you can do analysis, you have Haar measure, you have multiplicative Haar measure, you can integrate. On the other hand, this is an algebraic creature. There is only one prime in QP. Let ZP star be the group of units, the group of elements of absolute value 1. It turned out that any element in QP has the form x times u, x equals u times p to the k, where u is a unit, and k is either positive or negative integer. So QP, although constructed in a similar way to R, is different from R in many ways. Here is my favorite way manifestation of this difference. It turned out that infinite sequence of P-adic numbers is a Cauchy sequence if and only if the consecutive differences tends to 0. This means that a P-adic series converges if and only if the underlying series tends to 0. right? So this is any undergrad taking calculus trip coming through in the P-adic world, right? And let me show you how do we use the P-adics to solve actual questions related to rationals. So fix A1 to AN rational numbers, non-zero, and consider this equation. And ask yourself, when can we find a non-trivial solution? Of course, over R is over the field of real numbers, this is really easy, right? I mean, you just have to make sure that all the A's are not at the same sign. It's much harder problem to answer what's happening when will you have a solution over Q. And here is the answer. It has a non-trivial solution over Q if and only if it has a non-trivial solution over QP for all P, including the infinite prime, which is R. Okay? And it is a fact that if you do the local analysis, and QP are genuinely easier than Q, if you do the local analysis, it turns out that P-adically you can always solve it if N is equal or greater to 5, so you have only the real case to worry about. This is a prototype of what is called local to global principle. So you do some local analysis, local meaning on the local P-adic field and the Archimedean field, and then you somehow glue it together to get a global answer on Q. Q is a global object. And let me show you the other way around. There is also global to local principle. For a non-zero AB and QP, let's define the local Hilbert symbol. ABP is 1 if the equation x squared minus AY squared equal B has a solution in QP. And minus 1 otherwise. You can know that if you start with rationals, right, and the rationals are embedded in all the P-adic fields, then except for finitely many P, this is always 1. So we can take the infinite product. You tell us that this infinite product is 1. This is an example of global to local principle. If you know the Hilbert symbol on all P's but 1, then you also know that the last one, right? Moreover, this is nothing but a modern formulation of Gauss' quadratic reciprocity law. It is certainly not true that any local analysis is glued in a trivial way to a global result. For example, the equation in the center of Fermat's theorem is known to hold P-adically for all P, but there is no global solution. Typically, the obstruction from going to local, from local to global is some poles of functions called L functions. So the first examples were Dirichlet functions, which appears in the theorem about arithmetic progression. And among these, the basic example is the Riemann Zeta function. Right, so it is defined as this series for S which is greater than 1. It has an Euler expansion. It extends to a meromorphic function on C. And then it possesses a functional equation relating zeta S to zeta 1 minus S. So for instance, the fact that clearly when S tends to 1 you have a pole means that you have infinitely many primes, right? Otherwise this wouldn't diverge. So the analytic properties of the zeta function prove the Euclid theorem. By the beginning of the 20th century there were ample of L functions, each carrying arithmetic information. And all of them had these similar properties, Euler expansion and functional equations. And but to prove these properties at each given example involved more and more technicalities. In 1950, Tate corrected the situation by giving unified treatment to all the L functions. So he treated some huge ring which oversees all the P-adic fields and performed harmonic analysis over there. And there was a local portion to his thesis. He identified each term in the Euler product as a local L function. And I would like to give you some details about the local portion of the thesis. Let psi be a non-trivial additive character of QP. This is just a homomorphism from QP to the unit cosine circle. Let S be the space of Schwartz function on QP. namely the functions which are constantly locally constant and compactly supported. And we have the Fourier transform. You integrate against C. Let's speak now in the multiplicative character of the P-adic field. And for S, a complex number S, let's define the following zeta integral. So we start with the Schwarz function and we integrate it against x to the s, absolute value of x to the s, times chi x. And this is the multiplicative Haar measure. Okay. It turned out that this quotient of two zeta integrals is independent of phi. If we take the zeta integral from phi hat, chi inverse, and 1 minus s, and divided by chi, by the zeta phi chi s, the ratio does not depend on phi. Tate jump factor is defined to be this proportion factor. Okay? Right? If you take this quotient, then Tate jump factor is exactly this quotient. When you compute it, you end up with this integral. This may look like Gauss sum, right? Because we have here multiplicative guy and then additive guy. But it's not quite a Gauss sum since the integration is not over a compact subgroup. Let me record this integral because we'll see quite a bit of similar integrals. When you compute it, for instance, for chi which is trivial on the units, this is what you will end up with. So for example, for chi which is trivial, you actually see here this denominator from the Euler product of the zeta function, right? If chi p is 1, then this is 1 minus p to the minus s, and down here you will see the same thing, only you flip s to 1 minus s. So this kind of gives you a glimpse about the relation of this to Riemann zeta function, although I'm not saying anything about the actual proof. I would like to tell you now about the irreducibility result on SL2QP. So why to study SL2QP? So first, if you're a number theorist, then you can start with modular forms, which are solid 19th century number theory objects. And then by doing some quite technical but straightforward way, you can produce from them an object on this Adel ring, the same ring I mentioned a few minutes ago that Tate worked with. And then when you start doing the analysis, since this is not an abelian group, you will end up with doing an abelian harmonic analysis, which is representation theory. So SL2QP is a group of 2 by 2 matrices G over QP with determinant 1. Let's note that UQP, the subgroup of upper triangular unipotent matrices inside the SL2. Right, those are the elements of the code 1x01. Let HQP be the group of diagonal elements inside SL2. So it's easy to check that when you multiply these two matrices, you are adding these coordinates. So UQP is isomorphic to QP, to the other group. And HQP is isomorphic to the multiplicative subgroup, right? We have only one coordinate since it's SL2. And if you take the semi-direct product of the unipotent and the diagonal, you end up with the upper triangular matrices. U being normal inside the B. Let's denote this guy by W. This is a non-upper triangular matrix, right? It turns out that the identity in W is a complete set of representatives of the normalizer of the torus modulo the torus. And moreover, SL2 is generated by the torus, the unipotent, and this W guy. Given a character of QP star, we define a character of HQP this way, in a natural way. We should continue to denote this by chi. Now, in each context where you have a normalizer of the group, then it acts on the representation, on the characters. So we define chi W to be the character of HQP given by H goes to chi WHW inverse. It's really easy to multiply the matrices. It simply swaps A and A inverse. So, in other words, chi W is nothing but chi inverse. Okay? We can, since U is normal inside the upper triangular matrices, we can always extend the character. We can always extend the character chi to a character of the upper triangular by making it trivial on this coordinate. It actually works. And now here is the representation I would like to study. I will introduce it and then give a quick motivation why to study it. Define I chi. I will not use the notion of induction. This is just for those of us who know. I chi to be the space of complex functions from SL2 QP to C, smooth functions, so there is a topology here, with the following property. When you translate F by the left by an upper triangular matrix, it reacts by multiplying by chi, and forget about this one. This is just an innocent normalizing factor to make sure that this representation is unitary, given that chi is unitary. Okay. And why to study this one? First, by the very nature of the construction, when you start with a global object, it is the fact that in almost all places you will have either this one or a sub-quotient of it. So this is the first object to study if you want to do global theory. Of course, I forgot to say what is the action of the group. So the group G is acting on this space by right translation. Hence, we have representations of this. Okay. And here is a local motivation why to study these representations. So, a smooth representation of SL2Q3, let sigma be a smooth representation of SL2QP. A functional on this representation is called U invariant if whenever you hit your vector with the operator coming from the unipotent element, the functional does not see it. A smoothly reducible representation is called supercuspidal if it does not possess a non-zero U invariant functional. And it is the fact that a smooth irreducible representation is either supercuspidal or a constituent inside this induction, this I chi. This is by a very general argument called Frobenius reciprocity. So if you want to study the non-cuspidal part of the representation theory of SL2QP, you have to deal with this. And moreover, what I said just now holds also for finite fields, which is a really nice non-trivial example you can give to in first course in representation theory. So here are the natural problems. Find a criteria for this I chi to be irreducible. Namely, when do we know that we don't have any invariant subspaces? Describe the homomorphisms between two inductions. I mean, how much of a redundant do we have? I mean, how much repetitions do we have between different inductions? In particular, what's the commuting algebra of I chi and the homomorphism from I chi to itself? Bruhat theory tells us the easier part of the story. First, I chi has a Jordan Hesder of length 1 or 2. This bound 2 is coming from the fact that the normalizer of the terms has two elements. This may remind some of you Clifford theory. Second, I chi and I chi W, if they are conjugated by W, they have the same Jordan Hesder series, and otherwise, unless chi prime is equal chi or chi prime is chi W, they have nothing in common. Typically in this business, you get reducibilities, you get non-trivial intertwinings if there is some symmetry. So if chi is not preserved by conjugation, then the commuting algebra is one-dimensional. In particular, if chi is unitary, then chi squared not equal 1, right, which is what we have here, implies that I chi is irreducible. For unitary representations, having a commuting algebra which is one-dimensional is equivalent to being irreducible. So far everything I said is holds for the finite field, and in the finite field it will be the end of the story. It will be here if and only if. The first candidate for being reducible, the most symmetric kind will be the trivial character, right? It is the fact that I chi is irreducible, and I want to tell you why. I mean, in the finite field case, this would be reducible, and I want to explain why this one would be irreducible. Before that, let me discuss the intertwining operator. So I want to construct an operator from I chi to I chi inverse. I want to somehow change the equivariance with respect to chi, the equivariance with respect to chi inverse. And what is the nice thing to do? This would clearly take care of this, because when you may make the conjugation, you will get exactly what you want. But now we have the business of making the unipotent act trivially from the left. So why not do this? But of course, we are not talking about sum, because it's not a finite field case. So we have an integral. The point is that integrals do not always converge. So here is the standard trick in these cases. You induce a complex structure. You take your chi and you multiply it by up with 1 to the power s. And then chi is just chi 0, right? And we care about chi 0, but we have to care about all s. One constructs families of nice functions called the flat sections, such that for each s, fs lies in I chi s. And then we actually introduce this integral. This integral converges whenever it converges. And in fact, it is the fact that it converges to a rational function in p to the minus s. So we can take a neuromorphic extension. And away from the poles, this integral induces an SL2 QP map. Okay? So here is the intertwining operator we wanted. We can go, we start with I chi s, we integrate, and we end up with I chi minus 1 minus s whenever we don't have a pole. Note that we can apply it again. I mean, we can go back now using similar integral from I chi inverse to I chi, right? And unless, as we explained a few minutes ago, unless there is some symmetry, this would be irreducible. Meaning, for a Zariski open set inside the C, this is analytic at S. I mean, neuromorphic functions do not have too many poles. And the commuting algebra is one-dimensional. So if you compose these two, you end up with a self-intertwining operator. It must be a scalar map. And this scalar, this rational function, is called Plancherel measure. The Knapp-Stein dimension theorem tells us that the commuting algebra will be more than one-dimensional, namely 2, if and only if chi is symmetric, is invariant under W, and mu is analytic at S equals 0. So the whole question of reducibility, once you hit on a candidate, is to compute this function, to find its poles. So now moving to the question how to compute this one. I mean, how to compute this scalar. The naive approach would be to try and compute this integral, find a nice test function and compute it. This works for maybe for a subfamily of representation, but not for all. And I would like to discuss a different approach to this computation. So typically, what is more simple than analyzing a huge vector space like this induction is analyzing a space of functionals in this space, hopefully a finite dimensional space. So we have the notion of a Whittaker functional. Let C be a non-trivial additive character of QP, and let sigma V be a representation of SL2 QP. A functional C on V is called a Whittaker functional if whenever you hit V with a unipotent element, it is like multiplying CV by psi of X. Okay? Let me give you an example. So, how would you create a Whittaker functional on IKS? The reasonable thing to do is to integrate against sine inverse, right? This is formally will give us exactly what we need. But again, integrals do not always converge, so we again refer to this flat section. This integral converges absolutely to a polynomial in P to the minus S for some in some right plane. It clearly have the right property, right? If we now change variables, then you see exactly that it does the job. So the analytic continuation of this guy is a Whittaker functional on IKS. So I gave you one example of Whittaker functional on our induction. Denote by WH the space of Whittaker functionals on IKS. We know it's not empty because we have one example. Note that the intertwining operator that we introduced here, and I'm reminding you now, as always, it induces, when you have map between two spaces, it induces a map in the other direction between the functionals, right? So you will have a map from the Whittaker functionals on the target to the Whittaker functional on the domain simply by means of composition, right? Take the Whittaker functional here, compose on top of the intertwining operator, you end up with a Whittaker functional here, right? And clearly, if you're composing these maps on top, one on top of the other, you will get the same scalar we are chasing. So instead of computing the intertwining operator, we might as well understand this A hat, which acts on space of functions. And here is a very deep theorem in the theory of automorphic forms. Whittaker models are unique. This uniqueness implies, for example, that the automorphic L functions are Eulerian. They are responsible for the multiplicity, the global multiplicity 1 for GLN. And here it does mean that this A hat is a map between two one-dimensional spaces, right? Shahidi local coefficient is defined to be the scalar representing A hat. So this is a lifetime work started at 81 and never ended. I mean, there are 70 papers since then with 1800 citations. I mean, this proved to be one of the most productive way to treat L functions. So precisely, we have these two, we fixed the basis of these two one-dimensional spaces, and this is the scalar representing this map. And of course, the product of these two local coefficients, the Shahidi local coefficient, is what we are after, is this Planck-Charel measure. As opposed to the fact that we cannot compute this integral, we can actually compute quite easily these local coefficients. And the computation shows that CKSC is the meromorphic continuation of this integral, which is exactly this one, right? So this is quite remarkable that some rational function in P to the minus S that was defined using one uniqueness theorem is actually equal to another factor defined using completely different uniqueness theorem. This one came to explain the L functions, the Riemann Zeta functions, and this one came from the representation theory of SL2. This is quite remarkable, and in fact, by doing this trick with other groups, you can produce many more L functions. So Shahidi coefficients are Tate down factors. Just to finish the story about the irreducibility, so this is our mu chi-s since we know Tate down factor. So for example, if chi is trivial on the units, this is our rational function, meromorphic function, rational in P to the minus S. So for example, if you take chi to be the trivial character, then there is a pole when you plug S equals 0, right? Because you have here 1 minus 1, right? So this implies that I1 is irreducible. So in the finite field case, we would have reducibility, and the philosophy here following the Shapiro is start with the final field and then look for some poles. And here is the pole in this case. And for example, if you take another character which is trivial on the units, this guy. So now if you plug s equals 0, so this would be -1, right? So you will have here 2 times 2, so there is no pole, it's analytic, so the representation is reducible. By computing Shahidi local coefficient, one proves that given that chi is unitary, I chi is reducible if and only chi is a non-trivial quadratic character. And now we come to the object I like to study, the metaplectic groups. So what are the metaplectic groups? We have to assume that QP contains mu A, the full group of L throughs of 1. SL2 tilde is the central topological central extension of SL2 by mu M. So we have a non-split exact, short exact sequence. So this sits in the center, and this is a quotient. This is not a subgroup and not even close to being a subgroup. And the point is that for n greater or equal to 2, those are not group of matrices. You cannot embed them inside any GLM. And I wish to address the same question of reducibility of this representation. Okay? Here tau is an irreducible smooth representation of H theta, which is the inverse image of HQ in SL2QP, extended to the inverse image of the upper triangular inside the... Okay? Of course, I don't want anything that's coming by inflation from the linear group, so I'm assuming that the mu and the central die act faithfully. There is every chance in the world that the inverse image of the torus of the diagonal is not going to be commutative anymore. So we are talking about representations rather than characters. Although we understand this group, this is not an abelian group, but it's a two-step nilpotent group. So its representation theory is not too hard. It's a good question why to study them. So first, the n equal 2 case is actually a classical one. If you start with Jacobi theta function, you pretty quickly end up with the representation of this group. So this is actually, in a way, a classic. The n equal 2 case here is actually a classical case. Moreover, even if you are representation theory, you just look like local representation theory. So the first book which treats the representation theory of GL2 systematically was written in 1970 by Jacques and Langlands. And in that book, right after the introduction, they introduced the value representation, which is a faithful representation of the n equal 2 case of this creature. So, I mean, you cannot do theory of linear group without the metaplectic double cover. It's unavoidable. It's there. Okay? If you like it or not. So let me tell you something about the n equal 2 case, okay? Which is, in a way, the most basic example. HQP is commutative. It is a fact. And not unrelatedly, uniqueness of Whittaker model still holds for this representation. And much more generally, uniqueness of Whittaker functional hold for the double cover of SP2K, the metaplectic double cover of the symplectic group. This is a result I proved a few years ago. So, the metaplectic analog of Shahidi local coefficients for SP2 tilde, SP2K tilde can be defined and computed. This is another result of mine. Using a metaplectic Knapp-Stein dimension theorem, along with the computation of metaplectic Shahidi local coefficients, one proves that any genuine parabolic induction on SL2, the double cover, induced from a unitary data is irreducible. So the picture is not quite as in the linear case. I should say that the Knapp-Stein dimension theorem is not available in full generality at this point for covering groups. It is available for the case I'm telling you, which is a maximal parabolic induction, whatever that means. The research is now in the point where many people are trying to import results from the linear group to the covering groups. And the Knapp-Stein dimension theory is certainly one of the goals. Another one, for example, is the recent result of Bruhat and Chris Jensen about the Langlands quotient. So this is a fine classification of representation, which is known to hold for linear group, and now actually known to hold for covering groups. So here's what you get when you try to compute the metaplectic local coefficient. So let me note it by C tilde. You repeat the same game, and you will end up with this integral. So let's compare it to the Tate integral, which we already seen as the Shahidi local coefficient. The only difference in the Metaplectic case is that we have this guy, right? So what is this guy? This is an innocent map from QP star to C. In fact, it's fourth root of 1, with the property that it splits the Hilbert signal. This integral appeared first in the mid-90s in the work of J. Sweet on the general principal representation of double coupler of sp2k. He never published the results, and he never uploaded them. It just circulated between some friends. And I tried to find this guy, and I got very close, and I was told that he's doing something top secret for the army, and you are not allowed to get in touch with him ever. So
What's his name?
J. Sweet. So maybe there are some applications to this integral beyond what I know.
Classified.
Classified applications. When you compute this integral, this is roughly what you will get. When you actually compute the Plancherel measure, when you multiply two local coefficients, this for some reason goes away. For a long time, Shahidi, following Shahidi B also, thought that it was some freak of nature. But now I don't think so. This guy is actually important. Although it is this one who sets the tone for the Plancherel measure. So let's look at this integral again. In the linear case, this was Tate gamma factor. The integral representing Tate gamma factor. So here is a nice question. This kind of look like Tate integral. This equal to Shahidi local coefficients. So is there a metaplectic Tate gamma factor in the world? Is there such a theory? So it turned out there is. This is another result of mine. Start with the Schwartz function and define this weird transform. Okay? So you integrate again to C as we did before, but we also throw in this one. Typically, this will not be a Schwartz function. Nevertheless, with this integral, defining the Zeta integral, will converge in some vertical strip. This effect. So we can define the Zeta integral of this weird transform. And then it turned out that there is a proportion function exactly as in the case of Tate gamma factor, only which we are swapping phi hat with phi tilde. And when you go ahead and compute this proportion factor, you end up with Shahidi local coefficient. So there is complete analogy here. The metaplectic Tate gamma factor gives metaplectic Shahidi local coefficient. Tate theory has a global portion, and I do not know at this point what's the global portion of this factor. However, it recently surfaced. So now I do believe there is some life in this weird metaplectic gamma factor. I want to move to the case n greater than 2 now. People are interested in this mainly because there are two motivations. Some people like to create multiple Dirichlet series from these groups. It's actually possible. It's not what I do. And others are interested in extending the Langlands philosophy, the one governing the field of automorphic force, to covering groups. So this is being developed just these days. People are trying to reproduce the same conjectures and definitions. This is in the work of Weissman and Whittaker and Fangau, probably Gordon Sabin and many more. It is a fact that now the inverse image of the torus is not commutative. You need to submit a clear model phase. That generally nothing known in general about the dimension of these. This is probably finite dimensional. I did some work on double cover of GSP12, but generally it's not known. For this exactly, it's actually quite easy. It's D dimensional, where D is the n if n is odd, or n over 2 is if n is even. So, for example, when n is 1, then d is 1. This is uniqueness in the linear case. And when n is 2, then d is n over 2. This is the uniqueness in the n equal 2 case. In a joint work with David Goldberg, we've computed the matrix representing the map between the two spaces of Whittaker functionals with respect to some natural basis. Nothing much fancier than what I've shown you in the linear case. These matrix entries are high dimensional metaplectic analog to Shahidi local coefficients. And by multiplying these matrices, we covered again the explanatory measure. As a result, we've shown that given that tau is unitary, there are no reducibilities for even fold covers, and we found all reducibilities for odd fold covers. So for some reason, all the even fold cover behave alike and all the odd fold cover behave alike. I found it doing this honest computation, and then it turned out that this is predicted in my theory just being constructed by those guys trying to extend the Langlands philosophy. So there is Martin Weissman who is defining the L group of the cover group. I will not go ahead and tell you what's an L group, but this plays a huge role in the classification of representations. And what this guy shows that if the degree of the cover is odd, you get one L group for the SL2. If it is even, you get another L group. So actually, our result here with David Goldberg agrees with this predication by Weissman. And the point is that at this point there are not many evidence for this theory. This is a new theory, so I think ours is one of the first evidence here. I want to say really quickly something about the computation because there is a lot of arithmetic here. Let's see, for a fixed integers L and K, define Q, P, and K to be the guys whose P power equal to K modulo L. Okay? In other words, if you take the P-adic valuation and take the negative of the log, you end up with K. So this is one case, 1 over L of the field. When you're trying to compute the metaplectic Shahidi local coefficient, those matrix entries, so here is what you will see. So, suppose for this is not present here. So we have exactly the Tate integral, only we are integrating over some portion of the field and not over the field entirely. And this twisting is just innocent character of order n. So this look kind of again kind of Tate integral. So is this also a gamma factor? And when you're playing the same game for the even cases, then you end up with the same integral, only now you have this gamma psi inverse. So the question, do you have here another Tate theory? So we have defined the partial zeta integral. You integrate of this portion of the field. To compute the integrals in the odd cases, we have proven a functional equation of this form. So you relate partial zeta integral of phi hat to sum of partial zeta integrals of phi. The proportion factors are computed using the Tate gamma factor. Okay? The n equals 3 case of this was done in 1980 by a guy named Haluka. So this guy graduated from Johns Hopkins in '76, published one paper in 1980, and then he lived happily ever after in Washington DC, not doing mathematics. And it's quite, to be surprising that his work was overlooked. Especially that in '84, Knapp-Stein and Patterson ran into similar computation and computed them in a really brute force way, in a way that completely camouflages the arithmetic. So I was really surprised to find out about this paper and know that it completely escaped history. And last, when you want to do the even fold cases, then you end up playing the same game, only you're doing it with this metaplectic Tate gamma factor I had defined a few years ago. So this really makes me happy because in this game, it seems that Tate gamma factor and this metaplectic creature have equal standing. Really, if you're doing even for that cover, you end up with this. In a recent preprint of Martin Weissman, he asked whether Langlands-Shahidi method can be extended to a context where uniqueness of integer model fails. So this is not a positive answer, but this is something. This definitely shows there is an arithmetic here. There is a lot of global portion which I don't even know how to start, but it does show that there is an arithmetic here. And moreover, even before doing any global thing, there are many local applications, such as normalizing the intertwining operators, and reproducing Knapp-Stein patterns on the work on the exceptional representations.
What do you mean by an arithmetic?
So take gamma factor is an arithmetic creature, right? You define it using using Fourier transform, and I mean it tells you something about the L functions. So for me, it's an arithmetic creature.
I'm still not sure what that term means.
So here's what I. So by arithmetic, I mean so you have the L function, the L functions which come by from the Dirichlet character. These are arithmetic objects, right? I mean those are.
Well, I don't know. I don't know what an arithmetic object is.
Ah, okay. So this is what I mean. I think this is the.
This is the category. That's what you're asking, isn't it?
Maybe.
No, this is not the category. This is a title that oftentimes I hear people giving to this kind of object.
Okay.
So when you look at Knapp-Stein patterns of computation, you don't see anything of this kind. I mean, they computed that. They computed, but they don't identify their result as anything coming from Tate, the gamma factor, from anything that has anything to do with L functions.
Okay.
Okay?
Okay, so arithmetic means has something to do with L functions?
Yes, this is what
Okay.
I meant, and I probably did not choose my word.
I mean, if it's the term of the field, this is mathematics, I accept whatever definitions are given. That's fine. I just wanted to know what it was.
Thank you very much. Thank you very
So you gave everything over QP. Is it really over QP or?
No, it's work for over any number of fields. I mean, I just didn't want to take the trouble of explaining what's evaluated yet. But then you have to assume that the NP is in the n equals greater than 2, that NP are relatively prime. Yeah, it's not QP, it's any number of fields.
And then these matrices you computed, you said you computed matrices. Are they 2 by 2 matrices or how? What are the
Yeah,
matrices?
D by D.
D by D.
D by D, where D is n over 2.
Okay, dimension of that Whittaker.
Yes. And I expect to be able to reproduce it for any covering of quasi-split group or split group with no novel, not many new ideas. I mean, especially, I mean, definitely if you start with a cover of GLN and it's restricted, this is what I have in mind now, I'm able to do it for all other groups. And this is the very technical portion of the problem of extending Knapp methods on paper to other groups. So this is the main ingredient.
And do you really use that this group in the center is mu n? Is that needed, or it can be any extension with finite abelian group?
So I work with fairly concrete extensions.
You work
with
concrete.
Whittaker cycle here. And, and I think, no, I haven't yet seen other coverings. So I'm thinking about really those concrete examples coming from GLN, from restricting from GLN or.
Any other questions?
So are there generalizations to what you're talking about for SL2 to SLN for arbitrary n, or is that?
This is precisely what we are trying to do. Although I should say that the application for irreducibility is conditional upon having Knapp-Stein dimension theory, which we don't have. But for example, for SP2n, I did double cover of SP2n. I did it already, and although I mean you don't have Knapp-Stein dimension theorem, but I did it assuming Knapp-Stein dimension theorem, and Matic-Henzer did it. Hendel-Matic did it without assuming anything, so it is valid. And then I took their result and I made it work over GSP2 and double cover by some special relation between these two groups. So there are other examples.
And then with this, do you define L functions or for generic representations?
So I think that you should look for the eigenvalues of right. So you have these matrices. I have quite a good idea what will be the eigenvalue. So those are connected to be gamma factor. And I'm not sure, I mean, and I know how they differ by each other, how they differ. But this is quite a long way to do the global stuff, because I mean, you have to somehow cook Eulerian and integral, right? And I don't see at this point how to do it in general. Maybe for double couple of GSP2N, but it's something I'm thinking about, but I cannot say I know how to solve this problem at this point. But I'm very curious about it.
Any other questions? All right, let's thank our speakers.